And our claim is that in this case, G cannot have a normal subgroup of order 3. So we're going to suppose that H is just such a normal subgroup of order 3. And so in that case, the normalizer of H is equal to G because everything in G normalizes H. So since the order of H is equal to 3, without any other conditions at all, if the order of H is equal to 3, then it has to be a cyclic group. There's a unique cyclic group of order 3, and every cyclic group is abelian. So an abelian group is always contained inside of its centralizer, or the things that center it inside of G. Every element of H commutes with itself. So this condition turns out to be pretty powerful. So we can conclude then that 3 divides the centralizer, or the order of the centralizer, and then 3 must also divide the order of the normalizer, since we have H inside of each of these groups. So that means that if 3 divides the order of the centralizer, then the order of the centralizer has to equal 3, or it has to equal 39. And that's also true, by the way, for the order of the normalizer. Okay, the same things hold there as well. Okay, so we can look at 2 different cases. The first case is where the order of the centralizer is equal to 39. That is, it's equal to the entire group. So in this case, G is equal to the centralizer, and everything in G will commute with everything in H. So in that case, H has to be inside of the center of the group. Okay, and by the same reasoning, because 3 divides the order of H, the order of the center has to be equal to 3 or 39. But we know that H is not abelian, since that's what we assumed at the very beginning. Not since H is not abelian, but since G is not abelian. Okay, so that forces our center of the group to be of order 3. Should have some order signs on there. And the index of the center has to be equal to 13. Okay, so therefore, the order of the quotient group, G over Z, has to have prime order. So that means, in turn, that this quotient group is cyclic. Okay, now there's a theorem that we haven't discussed. The proof is way down in the bottom corner. It's the G over Z theorem, and it says that if G over Z is cyclic, which is exactly the situation we have here, then G is abelian. And I'll talk about that in a second. But this concludes that G is abelian, which is a contradiction to our assumption way up at the top, the very first thing that we said, that G is not abelian. Okay, so in this case, we have a contradiction. So the second case is the one that we went through in class. So just briefly, if the order of the centralizer of H is equal to 3, then in that case, the centralizer of H is equal to H. But then by the N over C theorem, this has to then be isomorphic to G over H. So we have C is isomorphic to H. Okay, and we know that this is isomorphic to something in the automorphism group of H. And the automorphism group of H, well, if we think about it, these are the automorphisms of 3 elements, okay? So what do we map 3 elements? So we have kind of maps of 3 to 3. How many different ways can we rearrange 3 elements? Well, there are 6 elements in the automorphism group. But the N over C, which is what we just said, is isomorphic to G over H, and that is going to have order 39 divided by 3, which is 13. And so we get a contradiction because we wanted that to be something that kind of plays well with 6, right? And we see that those things are just not going to work together. So we get another contradiction. So therefore the only options for the centralizer of H, that it's either 3 or that it has 39 elements, neither of those is true. So there cannot be any should have said normal subgroup of G of order 3. Oh yeah, I guess I put the normal condition there, but that was kind of a weird way to phrase it. So any normal subgroup of G of order 3. Okay, and then finally, to wrap this proof up, what is the G over Z theorem? Okay, well, it says, again, that if G over Z is cyclic, then G has to be abelian. So this just comes out of thinking about what a G over Z group might look like if it was cyclic. So if it's cyclic, it's going to have exactly one generator, and that's going to be of the form, a coset of Z. Okay, so if B and C are 2 other elements of the group, then they have to be of this form, because every single element in G over Z is of the form A times Z. Okay, but then that means that we can write those elements, so the cosets have to be equal to this. So that means the elements in turn have to have a nice interpretation for some elements Z and Y inside of the center. But exactly because this little Z and little Y are in the center, we can rearrange them. So when we try to put them together with some other element, or when we try to put them together, if we write BC, so BC would be equal to A to the M times Z times A to the N times Y. But we could rearrange those elements. Let me write that down. So A to the M times Z times A to the N times Y. Well, since Z is in the center and Y is in the center, we can swap them with the A's. So we could move them over so we could swap this A to the N, Z, and Y. And then the Y and the Z's can change positions as well. So I'm just going to swap them here. Y and Z. And of course the A to the power of M, A to the power of N, well, we can change those in any way we want to. This can be A to the power of N times A to the power of M. I had a Y, Z. And then I can swap the Y with the A to the power of M since it's in the center. Okay, and suddenly we see that this last line is equal to C times B. Okay, so this is how we can swap things when we have an abelian representation for the quotient group. So oftentimes the structure of the quotient group will say something about the structure of the original group.